Just a few words about me. So I'm working with Scala, I think already for 5 years. I was working before as Java. I think something like I'm a Java refugee, trying to always escape from Java. And last 2 or 3 years, I was still working with the Kubernetes extensively, and yeah, trying to basically combine JVM, Scala, and Kubernetes whenever I can. And I'm also like the functional programming. So to talk for today is around Kubernetes, obviously, and the writing the so-called operator for Kubernetes. Maybe before we continue, I would like to ask you guys who is basically working with Kubernetes on a daily, weekly, or on some regular basis.
Maybe write in the chat.
Yeah. Just for me to understand what I need to go deep in some explanation. Okay, so mainly we use Kubernetes, right? So in current setup, in current group. Okay, so yeah, Kubernetes operators. Within last 3 years, we have seen like a rise of operators. We've seen so-called Spark operator from Google, Apache Spark operator. There is something for Kafka from Confluent. There are other vendors or companies that released operator for Kafka, and many others, so-called operators for mainly, I would say, for stateful applications like databases such as Postgres, Cassandra, even CI servers, servers like Jenkins or any other applications like Prometheus. And there are also many support to developers from different programming language communities. So framework libraries in Go primarily, since Kubernetes is written in Go, and also in Rust, Java also at some point jumped on the bandwagon, and something in Scala, but it's also like with a question mark. So we'll see actually if it's today really easy to write something with Scala. Basically, you fall back to Java library and wrap in it. And also what I wanted to mention, since Kubernetes 1.16, which was released last year in September, the idea of so-called custom resource definition went from beta to general availability, and also to version 1. There is something that also was important. So we'll talk obviously, of course, about what operator means, what the custom resource definition means. But this is just a highlights like from the current situation, what's happening around the Kubernetes and the operators and custom resources in general. Also, GitHub made a website which is called Operator Hub.io to consolidate different operators, something like a marketplace or like a Docker Hub that you can imagine for, but only for operators, where you can upload your operator if you have a specific format. There's something like a bunch of shell scripts in the YAML file with reference to a Docker image on a Docker Hub that people can then take the scripts and install the operator from that Docker Hub with some more convenient way. And yeah, but what is actually operator in general or at all? So maybe before we look at operator pattern, let's recall how Kubernetes looks on the high level, its architecture and components. So as you might remember, there is the Kubernetes itself has a bunch of components in its architecture. There is a kube API server, there is a Kubernetes nodes, there is a Kubernetes master, so you can replicate each of these members. There are the kubelets on the Kubernetes nodes. There is a storage, which is etcd for all the resources, all the metadata flying around the Kubernetes world. There's a built-in controllers, and there's of course the API around that. So for operator, we are basically mainly interested in API server of the Kubernetes. So that's where we'll be focused today, on the usage of the API of kube API server. So operator pattern, what does it include? In a nutshell, you can describe operator pattern within 3 steps, within 3 main stages. So let's imagine that we have a Kubernetes cluster, which is on this page is a kube API server, and we have some so-called custom controller. So I will explain what does it mean soon. And the first step would be to basically create an operator or start preparation for the operator. Well, if you already have this operator, right, in terms of the custom controller, then the first step in order to use that this idea of operator, it would be to create a custom resource. So we know about the built-in resources like vault, deployment, replica set. In operator, we use custom resources, and the first step basically would be to send custom resources to kube API server, maybe through kubectl, for example. The utility that the command line interface that we all probably know. So what's happening afterwards? The second step in the flow of the operator pattern is basically there must be somewhere an application that is written by developers, so-called custom controller. So that's an application that is watching for custom resources, and whenever they appear, so basically it subscribes itself into a kube API server to watch for custom resources. Once they're there, custom controller receives them, and as a final step, as a reply, it creates the native resources. So basically, it's like you have some kind of definition of your application, but under the hood, on the low level, it consists of the deployments, of the replica set, of the many secrets, config maps, and other configuration that needs to be created afterwards. That definition basically means this kind of set of native resources. And also from the flow perspective, when we watch for custom resources, that is something that user wants to have. It's a desired state, but this is this declarative approach in the YAML spec, or, well, it could be also in a JSON, or some definition that we're taking from the kube API server. And the custom controller is basically trying to best to make this desired state to be actual state, so to be physical in Kubernetes cluster. Also, the custom controllers as synonymous to what people usually call in this paradigm or pattern as an operator. So this custom control you can call just an operator. So basically, it's an application running within Kubernetes cluster. So custom resource, what it may look like. In a YAML perspective, I think since we all use Kubernetes probably mainly with the Helm or with the just kubectl, so we've seen those many YAML files that will be still in this presentation. So in custom resource, if we take some imaginary operator for Kafka, then its custom resources could be called by something like a Kafka cluster, right? This field client is something like a type in Scala, in other languages. And inside this resource, we have something like a dynamic property called spec. So spec is your definition. What does it mean for this Kafka cluster? So it's completely up to the author of this Kafka cluster resource. So let's imagine that for the Kafka cluster, we want to deploy Kafka cluster, and our configuration looks like this. We want 3 brokers through the keepers. We want to enable security for SASL to have a KBRS there, KBRS authentication in and out and between the brokers. And we want to also enable TLS for Kafka security, so both security methods. And if you ever deployed Kafka on Kubernetes with a Helm chart, so manually, or you could imagine how it would look like. So typically, it's a stateful set with a bunch of config maps. So the stateful set for the keeper for Kafka, and what custom controller will do, operator, it will look at this custom resource, and since it's a written application running, it knows how to translate this custom resource definition into native resources. So this kind of native resources, again, if we look at them from YAML perspective, it's a set of built-in resources or native resources. In this case, It's, for example, two stateful sets for Zookeeper and Kafka itself, are services to have a routing for the brokers, some config maps to configure Kafka properties, Zookeeper properties, and ingress resources to export that through ingress controller. A bunch of other stuff. So that's kind of, we abstract away all this under the hood resources with just maybe one or two custom resources. So if we think now from developers' perspective, so what we need to do in order to build our own operator? So what would be the ingredients there? So minimum set is obviously Kubernetes cluster. So of course you can start with a minikube, but let's assume there's we have a Kubernetes cluster. So for starting with the development stage, we need to have at least two definitions. So here it's something like a red color: custom resource definition manifest and structural schema, which is in format OpenAPI v3, which is, as you might know, coming from the Swagger support, which is right now called OpenAPI. So these definitions, when you write, basically you can write them in, eventually you'll submit them to Kubernetes API server in YAML or JSON when you will be calling the API server. Yeah, probably I didn't say that. Kube API server in Kubernetes is basically a RESTful server. So it's a REST API. So these two definitions that we need to submit to register our operator will be written probably, will be serialized basically eventually to JSON or YAML, but you can of course write them in some programming language like Scala. And then on the development phase, we need some support, maybe some library, right? So to talk to Kubernetes, some REST client. So we don't want to compose the strings with their JSON bodies to send to some URLs. Probably want to have some more syntactic support. On the deployment side, once we develop that, we need to build an image of our operator, our application. So it will be some Docker image. And also we need to have deployment for our operator itself. So it's a manifest deployment for the operator. So that could be just a deployment spec or deployment resource. I can also make some replication of this operator. Basically, operator in simplest operator could be stateless. So you don't really need state for your operator. So as you will see, there's something like a function. So it's like a application that's something like reminds a streaming API that's received the events, translates them into something, and calls another service to create those resources. Yeah, and for operator itself, in order to watch for resources to create new resources on our behalf, we need to also set up airbag rules. Basically, I can show you an example, but this is just mainly the minimum set that we need to develop an operator. So from workflow perspective, again, let's review the flow. So we have Kube API server on the left, we have a custom controller on the right. So what's happening one by one? At the very beginning, our custom controller subscribing to custom resource updates. So it's a watch operation or watch endpoint, and API server pushing these updates to us. So we can use HTTP streaming, where we open long-term connection and the API server sending the messages to us. So we're listening for this. What's happening afterwards, let's jump to step 2. So we parse the JSON in case of Scala operator to case classes. That's probably the typical approach would be. And afterwards, we need to do some business logic in order to transform the customer resource definition or idea semantic into some native resources. So we create native resources by calling API server back. So this could be done asynchronously. It doesn't really matter. It's up to the operator. And also we update the status of custom resource. There's additional property on the custom resource. It's something like communication channel for users of custom resources where we can change the status, something like process or fail. So status is also up to the user. How did it call? What properties it has? And also useful property of the operator is reconciliation. So as you can see, this custom controller reminds something like an event-driven application where it's listening for changes, or maybe something like a Kafka consumer type of microservice where you get in events from some topic, you react on that, and you produce some other events. However, you may fail when you get these events. So in terms of Kafka, you probably can watch and from the previous subset, right? You can kind of have some options. And Kubernetes API, what you can do is kind of a reconciliation process. In order to do that, you can pull or just do some listing based on the intervals. You can pull from the API server by running just a command like get all custom resources, and whatever they are, they will be sent. There is, of course, some limitation and size of what the history of those custom resources will be arrived on the pool. There is also dependency to etcd configuration, how many of those custom resources it will keep, and history of them. But actually, yeah, it will return all of them which are there right now. So I think mainly there will be not that many of those custom resources because they abstract away many things. So it's not going to be like, I would say, shouldn't be more than maybe the pods in your Kubernetes cluster, right? Even if you, yeah, it depends on where you're working with Kubernetes, but if it's just some project for some enterprise, for some company that is using Kubernetes for something, there will be not that many of those resources, and especially custom resources. So there could be some issues if you pull too many resources or what to do with them, but let's skip this point for now. So I decided to bring some use case to do this and show together, do this together with you and show how some example, some operator could be done in Scala. So I decided to choose K8s Operator. So K8s, it's a solution for security to authenticate different services or users against some identity provider. I'm not sure if you guys worked with K8s before or not, so it's quite popular in Hadoop ecosystem and big data. It's used for a long time there. So K8s consist of a couple of processes or services which we pack as their containers in one pod. And now our operator, what it will do, basically, our operator here gets listened for custom resources specifically for K8s definition, and it creates, once it gets them, it creates a deployment for two services. One of them called is KDC, as a K8s distribution center, if I'm not mistaken, and K-admin. It's an additional service that allows to create new principals, new users there. And also in custom resource definition, we'll have something like a list of users, a principal that needs to be created. So eventually, from a native resources perspective, the operator will be creating a pod with a bunch of containers inside, basically two here, services, and a bunch of secrets. Every secret will be containing something like a credentials or a key tabs. So key tab in terms of K8s is something like your private key. If you're using SSH infrastructure, it's something like your password saved into the file, and something like a secret where you can authenticate against K8s without entering your password. So usually in big data world or Hadoop ecosystem, probably it's better to say key tabs are used by different applications to authenticate itself against K8s. And then when users are using these applications which are K8sed, they also verify whether that application I'm talking to is really that application that I know or not. So understanding of K8s doesn't really important for now for this talk, for this presentation, but just for us for common understanding. So the example of the custom resource definition, or basically a custom resource instance in this slide, could be the following. So we have our specific client, which I decided to call K8b. Every resource in Kubernetes, a custom one or not custom one, has these 3, I think 4 fields. So it's API version, client metadata with its own structure, and spec. So spec, as we said, it's up to the resource itself, up to the client. Since it's a custom client or custom resource, so we define the spec on our own. Before that, we need to provide a schema for this structure. So this schema, as I mentioned before, it's an open API v3 right now, and specifically for Kerberos definition. So what we need to have here in order to create something in Kubernetes as running Kerberos inside. So probably I must say that running Kerberos inside Kubernetes doesn't really make so much sense. I think maybe nobody is doing that. So it's just like an artificial idea, but it's kind of useful for development. So I'm specifically using this approach for development and some of the project, because having something like Active Directory where Kerberos is used natively as a backend solution for authentication, it could be quite expensive to run it somewhere in Kerberos or sorry, in Kubernetes, which might be not really feasible, or having a license for Active Directory to spin it up somewhere on the side. However, we having just a Kerberos without Active Directory, you can achieve a lot on your development while developing something where your application needs to be also talking to Kerberos services. That is why I took this example. Now coming back to this spec. So what we need to have here is something like a realm name, where we will create a Kerberos distribution center or this name of the realm, and list of principals, so something like a list of users, which have their names and passwords and yeah, names for the secrets. So basically, we have here 2 users with this name, and what this spec will mean that operator needs to create, first of all, this principal in Kerberos, and it needs to create a key tab for this user because it's configured here. You see they are a bit different because there are different configuration can be done. So I'll show you later what does it mean. It also, it has the section secret that basically means that Kubernetes secret will be created with this name, and type key tab, that means the key in the secret will be a key tab file. You know that in Kubernetes secret you may have just a string value, right? That's but you can create a secret from the file. That's what this spec means on the high level from the user perspective of the Kerberos operator that we're going to build. And the implementation in Scala may look the following way. So first of all, requirements. We want to parse the custom resources when they come into us to case classes, to Scala K classes. We also make it as functional and generic as possible. We want to use Cats-Effect and IO app in particular to watch for resource and yeah, do CRUD commands. On a higher level, the application, when we're thinking about this, I've put my thoughts on in this diagram, this maybe bizarre picture. So basically, the operator is something like a function from event of a particular type. There are 4 event types: is resource is added, modified, deleted, or as another 4th type, error. T as a spec, which we're going to receive, which we need to parse to case class, and the result of this function is a side effect, obviously, with a type of status. So we return back to Kubernetes status. We submit the status for specific resource ID for that custom resource that we caught. As I mentioned, this can be done asynchronously. So we received event and then we can queue it, right, and then later make this side effect and reply back with those native resources. Also, on the context on the side, besides the function, we need to have Kubernetes client support some library. We need to also have a definition of custom resource, the CRD. We also better to have a reconciliation on interval, where if we lost the event, so at least we will get it later and make the desired state actual state. We will pull the resources. So we watch for, there's a long-term connection watching for events from the Kube API server. So you can do that on, I'll tell it later. There are 2 technical things how you can watch for that. And you also maybe want to reconnect your operator If it fails, maybe you want to restart. And also for parsing case resources to case classes, maybe you also want to have pluggable JSON codecs, so maybe even in different libraries. If you want to parse them with a UJSON or a Cersei or a PlayJSON or other Scala JSON parser libraries. So in terms of the implementation of the CRD spec, and now we're switching from YAML to Scala. So how it would look like, that YAML definition that I shown before. First of all, the high-level class of the high-level class for that would be K8s. So I decided to, so you can call it basically anyhow. It will have these two properties realm that we've seen, a list of principals. The principal is another case class with its own properties. And some of these properties are two kind of enums, so ADTs, right? The first one is password, and another one is secret. So password has two options, which like a static and random, and secret has two options, keytab and password. So a secret that will be created eventually in Kubernetes can have two keys or one key. So if it's one key, that will be a keytab. If it's two keys, then it will be keytab and password. As for the status, we'll also model it as a case class, and case class, it's also up to the developer, up to the author of custom controller or operator. So let's have a couple of properties in the status, like Boolean flag, like that custom resource was processed or not, and two counters, how many principals were created since last modification of this custom resource, and what was the total, accumulated total, and there could be some error. Status can be seen if you run something like a command from kubectl or any other tool to describe custom resource, which is this K8s. It's already registered as a new resource, right? Usually you do something, describe something for a pod or for a config map, and you basically say like a config map name, same for custom resource. You say the custom resource name. In our case, it's K8s, and custom resource name, the instance of that. And what you will see, the output in CLI of kubectl, this property that you set before, and how this also this schema is regulated is part of that open API schema that I mentioned before. Also, there is also like a preview for you that the resource may have a predefined number of properties. There's a spec, status, and there's one more, if I'm not mistaken. Maybe they edited even more properties. But yeah, spec is an object which is up to the user, and basically you all specify the schema here. Same for status. In order to watch for resources which created in kubeAPI server on the custom control side, we have a possibility to use API server endpoint called, well, the parameter which exists in every endpoint called watch. Whether if we say that we want to watch and set this to 1, like a flag, to turn it on, then this response will be chunk response, so something like HTTP streaming, which will be long-term response for us. And this endpoint will be streaming to us these chunks of JSON. You see, there's like a different frames of JSON. So it's not an array; it's just literally frames. And what you may get there, if you, for example, watch for pods specifically, then you can see that there's some pod is added, modified, or deleted. So in any order, so you'll have this JSON definition of what created in Kubernetes, since you subscribe to this endpoint with specific parameters. Now let's model our controller, our operator. Main class or main handler. So I decided to model this as abstract class that has abstract methods and non-implemented methods for catching the events, actually on add, on modify, on delete. And it takes the custom resource, another case class, which encapsulates those properties that you've seen for metadata, for spec, and status. As you can see, also the spec is generic, and the status type is also generic. So this will be up to the user. As you remember, there was also some requirement that I said that we want to have this as generic as possible. So actually, new status is an option of some type U, where some resources or some operators, or it's up to you to have that status or not. So it's not mandatory. So if it's none, then there will be no that side effects sent back to Kubernetes to update the custom resource. And now if we take that for a K8s operator, we extend from that abstract class from the controller. We name our class as KB controller, and we specify those generic types. For spec type, we use our case class KB. For status type, we use our user-defined class status. So we can see how it looks like now with the non-generic types here. Yeah, we keep the effect type from the Cats effect as F, as generic. We only put a type class requirement that it needs to be implemented, have an instance of sync type class. And afterwards, we have this controller. We can instantiate it and implement some runtime that will launch this controller. Before running it, so what we need to have something like a Kubernetes client. This is a client from one of the Java library that we will discuss soon. And also we will probably need to have some configuration for CRD, because the CRD definition also has that configuration, which is usually supplied in YAML format, but we can also supply it where values or where the REST request to Kubernetes. And so we can deploy CRD definition on the startup of our operator, or we can, of course, deploy it separately, but then that would probably be deployed through the YAML manifest. And once we have all these dependencies, configuration, the controller instance itself, so control instance or this controller variable is a function from client to controller. That's basically says that this controller client creation is side effectful. When we create a client, it starts to look for kubeconfig and secrets, and for a service account. Yeah, in order to talk to Kubernetes and connect the Kube API server. So if we wrap it into the sync, we're delaying the creation. However, our controller also will need this client. That is why it's also in the arguments of our class that we called as a controller, the main controller that extends from abstract one. We'll get it back here. So we create it with this definition, but that will be passed then to us further here. Because in these methods on add, on modify, and delete, we will need this client again in order to reply to Kubernetes API server with those native resources. Or maybe later we will need it if we do this in asynchronous fashion. And then with some runtime, which I decided to call operator of CRD, we start this operator. Once again, the types of this kind of helper method. Then how our program could look like from the Cats effect perspective. So we extend from IO. We have some operator that can be ran. It returns IO of exit code. This operator class itself has this run method that again returns f of exit code, and it has some bunch of parameters and type class instances. So we will look at what could be inside further. Before maybe showing the examples of the code of the real operator, I also wanted to describe some challenges, what I found by using one of the library as a client for talking to Kubernetes. So there are right now a couple of libraries, Kubernetes clients in the JVM or for Scala, Java community and Scala community. So one of them, which I decided to use for implementation of K8s Operator, is Kubernetes client from Fabric 8 project. As it's Java library, so you need to be prepared from the very beginning that it has surprises, something like basically many Java libraries have is a null pointer, so returning nulls in some places or throwing in exceptions. So basically when you bridge from Scala to Java library, you always kind of wrap that stuff into a try or either option, basically to catch that side effects or nulls and whatever. For example, there's a snippet of code that previews the API of this library. So if you want to list the pods or find some pod which is not deleted, and what you do is you have this client. There's a Fluent API that you say, okay, I want the pods in this namespace with this label, and then I call list, which is running request to the server. Then result is gets back, and then list may have some surprises. Some could be null, something like that, or exception. Then you get the items out of it. That's finally a Java list. Then you convert maybe to Scala, and then you do something with that. In order to watch for resources, for custom resources, or for any resource, this library provides some API called Watcher. So what you can do with that, once you have that client, there's a specific method called custom resources, where you say what class needs to be used to serialize those received events to. There's a specific type that I defined, which is called any custom resource. Then once you have this CRD client, you can call once again on it the specific method watch, provide the implementation of the interface called Watcher. So it's typed interface. As you can see, there's any custom resource that already repeats here. And it has two methods, like event received and unclose. So that's the callback for us, or the way how do we listen for events from the Kube API server. So we don't necessarily need to call that chunked request response idea that I've shown you on the slide before, but in this library you can do this like that. The first problem appear here once we're coming from Scala and from the Cats-Effect perspective, that this API from the Kubernetes client library, from Java library, has this return type here as unit. So if we want to make this IO idea of this F effect all the way down without the side effects, so we have to somehow run that IO, right? That will be responsible for catching the event and processing it somehow. But it returns unit, and it's becomes a problem because this API, probably I will show this on the next slide. Yeah, this API is here, instead of question mark, there will be some code that will be doing something with the custom resource that is called by the client. So in order to run some command, again in a functional way using effect library like Cats-Effect, you would work with F of IO, but since it's unit, you would need to maybe run something like unsafe run sync, right? Or basically evaluate side effect inside, instead of delegating that up to the IO app, right? Which is running some run loop at the very end of the world and evaluating those IO which you are producing in your Cats.io application. So here we're kind of broken with this API, but let's see what we can do. The second problem with this library is that you've seen when we create this CRD client by calling one more method on a regular client, we have to supply the class that will be used to serialize receive JSON into, and it supports actually. So how does it look like? This custom resource from this library, you extend this class. You can call your class anyhow, and you can put any name. And the body of that custom resource that you're interested in it's mainly spec property, right? That is why we have these fields here like spec and status. So we can catch a resource that was already created and modified or updated many times. So on the next receive the same of event, we already have a status which will be non-empty. That's why we also want to have it as on the receiver side. So it supports instead of any ref, you can also put generic types here like T or U. So, but how does it work? So under the hood, this library is bound with a JSON JSON library, Java library to parse JSONs into Pojo. As you might know, JSON also has a Scala module, which aware about the case classes, how to properly serialize, deserialize JSON into the case classes, because it's a bit more work for a library to properly serialize, like maybe ADTs or all these polymorphic types. So simple or regular JSON doesn't understand that. So you need to also bring that library as well. And also it bound basically us to only to JSON. If you want to use something like source, we need to think build some solution for that. That's another problem. So instead of using maybe this T and U, well, even if you use this generic type here, that anyways using reflection, and it will be casting by end of the day, and that becomes a bit also a problem. So let's see how we can tackle these problems with this library. So first of all, there's a problem of void, right? We have that unit return type in Java, it's void. Once again, that piece of code that we've seen in that Java library, it has some kind of in its own source code, some watch method that calls our method our code that we wrote. So typically, what this code would be in Scala, where when you write your operator, you have that instance of the custom resource. In our case, that any custom resource, you parse it, right? You have maybe some JSON parser here. Then you have that's basically no side effects here. There's just a parsing, and then it's either it's parsed normally. It will be custom resource with T and U and either error. And then we want maybe also to handle the events asynchronously. So we have something like some consumer where we put this parsed action or event to it, and then consumer will be creating all those native resources back to API server. So we want to have all the parts with control side effects. So we're working inside of IO. That consumer is basically also, for example, written with the Cats effect, where we put action, it returns f of unit, right? Some consumer that mutates, but it returns your an IO back. So that's IO back returned here. However, that's the void. So if this IO won't be evaluated, it will be discarded by JVM, by garbage collector as a useless value. So there will be no handling of the events if this void is here. Yeah, so the question is, can Kubernetes client evaluate the effect on its own? Obviously not. So what we can do, what I found the single way in order to tackle that is basically to run the side effect here on a producer side. There's an effect type class in Cats effect that has two IO method. And it can transform some f of a to IO if that f has type class for effect, instance for effect type class. So in our case, how we can use that, how it is useful for us. So if we have that sync instance, which is called here as f, we can call to IO this side effectful value. We will transform it to IO type, to this one, to Cats effect IO. And then we have to evaluate that here on the producer side, basically calling unsafe run sync. And then we will have this A value. So in case of put in action, the A value will be unit, but we achieve the result of that we put that action further to consumer. So consumer that will create all those custom resources and further stuff. Yeah, we can also call this function not put action, but put action blocking. Sorry. And then, yeah, it will be returned a unit. We call this run sync. Afterwards, we put the action. So we evaluate the effect of the put action here that we have to do. And we solve the first problem of this library. Second problem with JSON serialization to case classes is so a bit more about the problem. So if you look at in the debugger where this library is deserializing the events into your class, so the the idea of deserialization in this library that you provide your POJO, right, the plain old Java object. But in our case, it's something like written in Scala with this var and underline undefined values. If you look at it in the debugger when it's restoring or making a deserialization of the values from the network, you will see that Jackson is doing that as a linked hash map. So basically, JSON representation in Jackson is a hash map, it's a linked hash map where the key is a key of JSON property, a name or value is a value of that property. And then it tries to cast it to that type that will be here. Even if you put these generic types like T and U, in our case, it will fail if you will not supply in runtime the Jackson Scala module library. So it won't really deserialize these classes properly, especially with those ADTs that we've seen on this spec. So what we can do, we can use Jackson API to intercept the deserialization and kind of prevent it from deserialization to classes, but keep it as a string. So what it has is, so we can define our own case class called string property, something like wrapper around the string. Then there is an annotation from the Jackson that you can say this is a JSON deserializer for this type. And eventually, you also need to define deserializer. This deserializer will be registered in runtime by this library. And whenever this library needs to deserialize that event into this class, it will see, I have this string property here, so I've seen that somebody registered a deserializer for it. Okay, I will go there. It will find this deserializer instance and specifically deserialize method, and we'll use it to convert something from JSON parsing and the context to the value. So what we can, so we're cheating here. We take that AST of Jackson, right, the representation of Jackson of JSON in memory, and take that as a toString and return it back as a string property. So we kind of preserve that it's still in string. We do not deserialize. And if we look at the value right now of this string here, that will be JSON. And what we can do now, we can plug our Scala JSON library, right? We want to deserialize with a proper Scala library that doesn't need any other stuff there. And eventually, you can parse these properties individually from the custom resource and turn them in the proper types, right? By parsing them to this KRB or status that we've seen initially. And how this parsing property function could look like is we take the string property and from some JSON reader, some abstract JSON reader that we take as a type class instance with this implicitly keyword or a method. We from this reader we read that from string to a specific type of T, which in this example that would be first we call it with a KRB and then with status. So basically what we've done one more time is we prevented Jackson from deserializing that into some stuff, which would be a bit useless or would require some additional configuration. We said like keep it as a string, so we'll deserialize ourselves manually later, and that we will do as the next step. And if you want to know what that mysterious JSON reader is, basically a kind of bridge between our implementation of the custom controller and any other library. So here we can plug in sourcey, a JSON library, to parse string with its decode method to a type, to a case class. In order to parse our case classes from sourcey perspective, we mainly parse everything with auto derivation of the sourcey codecs for our case classes, but some stuff like ADTs would need to define at least decoders for those ADTs. And also we want to parse this and deserialize the ADTs with the discriminator property called type, where for objects with no properties, that's quite useful and probably one of the way to deserialize and serialize those Scala case objects. And the final API, so if we think on the generic implementation, would look like this. So we have this K8s Operator application. So we start and we call it as a K8s Operator. We extend it from IO app. We have those source codecs. We have a run method inside where we schedule some operator runtime. We pass all the required dependencies like configuration, Kubernetes client, controller, which is the controller is your abstract class, not abstract class, but something that extends that abstract class. And we also may have additional combinators to enhance this operator runtime that we want to say that we want to start reconciliation process for every 60 seconds. And maybe want to also restart if it's failing. So if this IO going back here, if it will be failed, right? And exit code will be returned, this application will be shut down. So to prevent that, we can intercept that maybe somehow this runtime and say that, okay, restart 3 times and then maybe give up and propagate the failure to Kubernetes pod, which will be restarted automatically by Kubernetes. So I will probably show you how does it K8s Operator implemented in real code. So far I've shown you only pieces of this idea, but before that I also want to show you how easy basically is to do different things in Cats-Effect for this task that we've got from operator application implementation. So for reconciliation process, to do reconciliation of the events from the Kubernetes API, we can implement something like a class called reconciler, where it has some task that we can run like a flat map, right? That returns a resource list or error. And we can do that in a loop, in a recursion. So this reconciler may have a method called run, where what we do inside of F is we do some sleep or some delay that will be, for example, our 60 seconds. Then we flat map that current resources, we get the resource list. So basically we run that IO every time. That IO current resources is basically running the list method on the client that getting all the custom resources from the Kubernetes operator. And once this list is in our hands, we publish this list to a consumer. So that's the only responsibility of reconciler, which is just to pull in the stuff, slipping, and publishing further to process the resources. If it failed, we intercept, we log some error here, and then we return the exit code. It goes up to the method signature, right? And then it propagates up to the IO app, and so the IO app will crash if it's a Kubernetes application. Obviously, it is because it's an operator running inside the cluster as a pod. That will be restarted, and the operator will again recover and will connect for watching the events. And we'll do this reconciliation loop. As for the restart, it's also quite simple to do that. This idea of, so as you might know in Cats-Effect, once you're, for example, if you're familiar with our web servers like HTTP4S, then how does it work? It's running long-term server IO that like never terminates, ideally, if it's not crashed or failed. And the idea of K8s Operator in general here in Scala with Cats.io, Cats-Effect will be similar, like we're on HTTP4S server, right? So we run it and it's listening for those events infinitely. If it fails by some reason, so IO app will be shut down. For doing a restart, so what we can do, as you might remember, we have that run method, right, that returns an exit code. Run method, it started our watch, our listener to API server. However, when it fails, basically when IO is completed and return that exit code, so what we can do, we can flat map it and call some function like a loop, where the loop function is calling again with restart. So basically it's a recursion and it's running method run again. And again, it's waits, connects the operator to API server. And in a loop, what we can do is we have maybe initial exit code. We have some notion of retry, some case class that describes what is retry in terms of the parameters and delays. So before looping, we may also have some delay before starting the operator again. We calculate next retry. So if it's incremental or random, that will be calculated next retry value, like how much time next time we need to sleep, or how many retries left, depends on the strategy. And then we call it with restart. So we again listening here or running here, maybe infinitely, right, until we crash. And then again, we flat map and loop. So that's how you can do this with recursion. We can implement the restart of your long-running task in Cats.io. And I decided all this stuff make as generic and make as a library. And I published this library to GitHub, which I called Freya, and it's available on this URL, which is something like a Kubernetes operator library for Scala, where you can have the generic classes and this controller and this small runtime, and you plug in your case classes. That is why you have this generic types like a T and U that we've seen on the slides. And implement your controller that actually will be your business logic. It's up to you. So the library helps you to kind of speed up with the runtime, with the ramp up of the operator. It has the main core method module. It has two other modules if you want to parse your case classes with sourcey, or you want to parse that with checksum. There's a possibility to extend the number of support of other JSON libraries as well. So it has some documentation also. Besides that, I implemented this runtime that I've kind of previewed for you, right? This with restart, with reconciliation, and that run method that we haven't seen so far, what it's doing inside. But from the high level, what it's doing is actually running that IO app and the watcher and reconciliation. There are two tasks which are reconciliation are backed fully by Cats.io context shift, by the executor or thread pool by the Cats effect, and the watcher partially backed by Kubernetes client Java library, which is backed by OK HTTP stuff library, which is inside the Kubernetes client, which has own thread pool. As you remember here, we're running the side effect, like putting the action blocking. And eventually, it's there is asynchronous consumer of the events, which has something like queue per namespace. So it's handling the custom resources in parallel, concurrently per namespace. So basically, if different namespace in the same time create custom resources of this type, the operator will be called concurrently. So it needs to be thread safe. Also, while developing this runtime, I found another interesting thing, that it's quite easy to do different concurrent data structures with Cats effects, such as blocking queue. The Cats effect provides a couple of kind of low-level primitives for concurrency, and some of them is ref and mvar. And in terms of the blocking queue, which is used by Freya to implement consumer and producer. So producer is the watcher that takes the event from Kubernetes and puts to the queue, and consumer is a kind of processor that converts the events to the native resources and publishing them back to Kube API server. So you can imagine that the kind of classical blocking queue has something like method to produce and consume. So they both return F task for IO with a unit type, and also consumer may say, I don't want to consume anymore, by returning F of false, by signaling to this queue that it needs to be not consumed anymore. So this blocking queue, as you might know, how does it work? It blocks producer if there is there's nobody to consume, or if the queue is full, and it also blocks blocks producer, and it blocks consumer if there's nothing to drain, nothing to take, and it doesn't block if there are queue is empty. Sorry, queue is not empty for consumer when it can basically drain without blocking. So it's quite useful data structure for building something like a channels to communicate between the threads. So in order to implement, you can use basically in ref and in var, where the ref is may keep mutable queue, mutable Scala queue. So property size is basically a size of this blocking queue. And signal is used to communicate between producer and consumer, to signal there's something there I need to consume, or signal that I'm ready to consume to producer. And a bit of documentation from the Cats effect. What is ref is basically pure atomic reference, right? So you can build more complex data structures using it. And mvar is it's something like concurrent queue, and it has only one element. So the queue of buffer size 1. So it mutable location that can be empty, and reader is blocked on empty, writer is blocked on full. So something like a queue of one element that you can pass between two different threads. And how I implemented that perhaps not the most efficient implementation of the blocking queue, but in terms of the producer, we have this queue, which is a ref. Ref has modifier modify, that gives you back queue, which is this queue. It's just a Scala mutable queue from the collection of Scala, from collection package. And what we do here is we check the capacity of the queue is not full. We enqueue that new element, and we say that we enqueued by returning a Boolean. If it's full, we return the same queue without modifying it, and we return false. Then later we analyze the flag if it's added. Then we signal with the mref method called tryput, which we use value just a unit. You see this two parentheses. So we don't really need to put any value. This is just a signal that we need to put the call or put that will be later used by consumer because it may block on the getting new element. That will be it will be like a wake up for a consumer. Otherwise, if it's not added, we need to do something like back pressure. So we are right now in consumer. We cannot put to the queue because it's full. So on else, we put blocking. So the put will be now blocking. So we put some, again, unit. And we wait for a consumer until it calls another method, which is a dual or alternative to that method is take. So we'll be blocked here until consumer will take something from the queue. Once it's going to be taken, then this will be evaluated, and the next effect will be again produced. So it's a recursive function. So we will produce the stuff. Well, yeah. If we couldn't put first time, we'll try to retry until we succeed, until we go to this branch. From consumer side, what we have here is we have a queue that we want to take something from it. So we call the modify on the ref. We have a queue out of it, this queue letter. And then we take the head of the queue using the queue option. So if there is something there, if it's queue non-empty, we process it with the map. And what we get out of it is an element, which is a queue. The rest of the queue is a queue letter again. And then we return back to the modify the state of the next of this queue, which is again queue later. And we say again that the element that we took, we model this as an option, so this will be sum. If queue was empty, we return the same queue and none. Later, what we do, we analyze this element. If we took something, there was something in this queue, then we call that function that consumer supplies to us, right? So that's f. This is something that will be in your controller. We pass this element there. It returns f. Then we analyze if it wants to continue to consume this queue. Then we consume it again. So we call the consume again using this combinator when a. If continue was false, we don't call this consume anymore. So we return from this consumer function. That's it. If there was some, if the queue was empty, Then we go into blocking by calling take method on the mvar. And until producer calls put, this will be blocked. Once consumer called put, this will be woken up, and then we go again to consume. Basically, producer can wakes us up, and then we go to next round and consume, and we'll find new element there. And that's it. That's what you need to implement something like a blocking queue and Cats effect. Are there any questions so far? As we're already closing, close to finish.
I have some for later.
Okay. So besides these different things from Cats effect, the our operator also has some configuration which could be modeled in if it would be YAML, it's just a different properties in the CRD definition. However, you can also model that as a case class with a bunch of parameters. And eventually this stuff can be used to deploy the CRD definition to the Kubernetes operator. There are different things like namespace where we want to start operator to listen to new events for. So usually operator started for all namespaces, or you can say, okay, I want to listen only in this namespace, like default maybe, and that's it. For the runtime for dispatching the events in this library, I modeled like two properties, the queue size, and you can switch off this concurrent distribution of the effects or handling of the producer and concurrently, so it could be false or true. And different properties for your CRD, the API group like prefix. So you have to supply that as well when you register your CRD. Different configuration for short names, plural names of your registered CRD, and additional printer columns as well. Also, besides the custom resource-based operator logic, we can actually model that as a config map as well. You might maybe already found yourself that CRD is something like the custom configuration that sits in the Kubernetes or configuration or resource. It could be easily also put into config map, right? There's a map for configuration. So it could be put as under some key, like here we have config key, and there's some structure, which also could be a JSON that you can parse. And then you can watch for these config maps, and basically that's the second feature that this library supports. You can start operator based on config maps. So why it could be needed is maybe by some reason in your project or Kubernetes you can't register custom resources because you need some rights from admin, for example, of this Kubernetes cluster. You also need to add airbag rules for your operator. But for config map is much easier, so you don't need all those rights. Let's can easily implement that on a config map. But the one downside of using the config maps as a modeling resource of the operator or custom controller, that you can't see them, so you don't benefit from the separate notion that you can list custom resources in kubectl as a separate class of resources. You can't see them in those different UI dashboards. And you also don't benefit from validation schema of your custom resource that it's in custom resource definitions. So here you would need to validate yourself or whenever you catching the events. However, for the CRD, for custom resources, the invalid resources will be rejected even on the stage of creating those resources. So for example, somebody creates that CR instance of KRB with kubectl, and if there's something invalid from the name perspective or syntax of this spec in YAML, it will be rejected, so it won't be created. So your operator will be even not aware that somebody tried to create invalid resource. There's an example of this operator re-implemented, and it's working and tested in some project, and you can find on this URL. The idea of this writing this operator for Kerberos basically for two purposes: is to implement so-called ASP.NEGO authentication. There's one of the RFC for this authentication exists, And another one, if you want to have your application which are talking to Hadoop world, or basically to, not necessarily to Hadoop world, to something that is protected by Active Directory with a Kerberos protocol, you might want to have our key tabs, which you would need to mount as secrets to your Kubernetes applications. That this operator can do this secrets with the key tabs inside for you automatically based on the definition of the custom resource. Also, regarding the Kubernetes client library, there was some library when I started to write in the library, my library, and that operator called Kubernetes client from this address, from this GitHub account. And however, it was missing some support of APIs based on HTTP4S, Cats-Effects, and SRC. So exactly what I was looking for, but it was missing important APIs, Kubernetes APIs that I couldn't use in this library, and I decided to choose the Fabricate library. So it was actually missing these APIs that I needed, and maybe within spring, I added that support, basically contributed a couple of pull requests to the library to support a bunch of more stuff. And more importantly, it was missing custom resource definitions, custom resources in general, and watchers. So many things that prevents you to write operator using this library. But it was quite nice library actually, and quite small one, well done. But yeah, it was done for mainly for kind of DevOps perspective. But now it's also usable for building operators. So now we basically have a choice using this my library or this one directly. And that's it basically. So if you have any question, please ask right now.
Thank you very much, Lexi. Any questions? Otherwise, I will start with my first one. So I was wondering, you on one slide you had the HTTP API for the watch call, and if the Fabric client is such a pain, I wondered why you didn't replace it by just using a normal HTTP call, using, for example, the HTTP4S client, and then just pass the stream there.
Mm-hmm. Yeah, this could be an option. Actually, I didn't think about this way. This would be an option as well. Yeah, HTTPS client has so the second library, which is a Scala one, is using HTTPS exactly in this way. You can run watch requests using HTTP streams there, which is I believe HTTPS is doing that through FS2. Yeah, so you could do that. That's exactly what I've done actually in that library as a pull request. Yeah, and doing that in my library, that could be also working. That's would be probably the same idea. Yeah, that library actually, the Fabricate, allows you also to do a bunch of more stuff to deploy custom resource definition a bit easily, and some other features. That probably was the reason why I stopped on it. Yeah, but yeah, good idea.
Interesting. Okay. Any other questions? I have a follow-up. So I was thinking about, so if you use the Fabricate client and you have this problem of the callbacks, right? That you are only getting pushed these callback methods that return unit. As far as I know, FS2 has even support for handling callback APIs by using a bounded queue or maybe even an unbounded queue. So it might be possible to just replace your custom queue solution with the built-in one from FS2, and then you would get back the FS2 stream that you can run on your own. So you don't have to execute the IOs on every callback.
Could be. I also didn't want to use FS2 because I wanted to minimize number of dependencies to my library. So that's probably was the main reason why I didn't use. I actually yeah, before doing this blocking EQ and many other stuff in the runtime, then in Freya, I was thinking to use FS2 because it's really a really good library with all these primitives. But yeah, the idea was to basically build the library without that much dependencies. So it already depends on Cats-Effect, obviously, and I believe on Scala logging, or yeah, there's some logging there, and something else, like 2 or 3 stuff.
Yeah, you might want to play around with that. It's really cool for even for converting such callback APIs.
Yeah.
You also get back pressure and stuff like that.
Yeah. Yeah, let me see what are the dependencies. They're not here.
And something that I didn't get was, how do you implement the partitioning by namespace?
Mm-hmm. So for partitioning, actually, yeah, let me come back to that slide. It was probably the most complex task in this library to do that. So there is a hash map of the queues where the hash map is also growing in terms of the keys. So the key of the hash map is the namespace name.
Yes.
And every value, it's I think it's a list or something like that, a queue. Yeah, I think that's that blocking queue actually or something. Yeah, and there's back pressures on every queue, and but it doesn't think back pressure on a number of namespace. Probably doesn't really make sense. So if we imagine that would be like so many namespaces, that yeah, that hash map will grow.
Yeah.
But yeah, that's how it is done.
So something that you could also try there is, I think FS2 also supports this to partition a stream.
I think
by keys,
so.
but
Yeah.
I'm not completely sure. I didn't try, but I know that at least in Akka streams there's something like that which works exactly like this. So there should be something like this in FS2 as well. So maybe it would be worth a try to just replace it with FS2, and then I think there is something to partition it, and then you would get rid of a lot of code, maybe.
Maybe, yeah, but that was
an idea. I don't know.
Yeah. Again, I agree with you. That's FS2 is a nice library, and probably would make sense. My rule of thumb was basically, if I would write an application like a K8s Operator, which is another project, I use any libraries that I can find. But if I write my library, a new library that will be used potentially by other people, then I try to minimize the number of libraries that I need to depend on. And the second idea was basically to learn a bit the Cats effect, how to do all this stuff manually. That was the reason that some of the stuff I implemented manually without using FS2. So those primitives like MWAR or ref, some of them are even migrated from FS2 or from Monix. It's even written in the Cats effect documentation. Yeah, but obviously, yeah, there's a blocking queue for sure in FS2. It's quite comprehensive implementation there.
So I would not want to integrate Akka in this dependency because that would be hell. But I